GPU Architecture, Structure, Components, and Working of Graphic Processing Units by Tejas, Pranshu, and Viraj. Introduction to GPU Architecture. What is a GPU? A graphic processing unit is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images, simulation, and parallel computations. GPU leverages thousands of smaller, efficient cores that can handle multitasking. This throughout orients design makes them an ideal for processing vast amounts of data in parallel rather than focusing on minimizing latency for single tasks. Initially, GPUs were developed for primarily for 2D graphic acceleration in personal computers. Over time, their architecture evolved significantly, transforming them into highly parallel programmable processors. Today, GPUs are indispensable in diverse fields such as AI, scientific research, data analysis, and high performance computing, driving innovation across industries. CPU, Central Processing Unit, as we know, GPU, Graphic Processing Unit. Cores, few 2 to 16 powerful cores, and in GPU, thousands of simpler, smaller cores. CPU, the optimization is a bit different. Low latency and sequential performance in GPU, high through output, parallel performance. Task type, CPU provides a general purpose single thread tasks and etc. Whereas GPU with data etc. CPUs are best for operating systems, application, and complex logic, whereas GPUs are better for rendering, AI, and simulations and HPC.
So now exploring the type of GPUs. First is integrated GPU or iGPU. Built directly into the same chip as the CPU. iGPUs share system RAM with CPU, making them a cost-effective and power-efficient solution for general multimedia tasks and light computing. However, their performance for heavy workload is limited by shared memory bandwidth. Now next, let's talk about discrete GPU or DGPU. A DGPU is a separate hardware card installed in a PCIe slot equipped with its own dedicated VRAM or video RAM. This design allows for high performance in 3D rendering, AI, and simulations, but comes with higher cost and power consumption. Now, next, we have multi GPU systems. These systems link two or more GPUs using technologies like NVIDIA's SLI or AMD's Crossfire. Multi GPU setups are typically found in extreme gaming rigs, scientific computing clusters, and render farms, pushing the boundaries of computational power. The choice of GPU type depends heavily on the intended application, balancing performance needs with budget and power considerations. Now next we have high level GPU architecture overview. So basically, first let's talk about the graphic processing clusters or the GPCs. These are top level organizational units within a GPU, each containing multiple streaming multiprocessor or SMs. GPCs manage the overall graphic pipeline and computation tasks. Now let's understand SMs or the streaming multiprocessors. SMs are the heart of parallel execution in a GPU. Each SM houses numerous CUDA cores, special function units, and memory components executing instructions in parallel. CUDA cores or ALUs. The fundamental processing units within an SM are the CUDA cores or the ALUs, arithmetic logical units, are responsible for the performing integer and floating point calculations, handling the core computational workload. Now, let's have a deep dive into streaming multiprocessor or SMs. What are the components of an SM? First is the CUDA core. These are the primary processing units that execute arithmetic and logical operation. GPUs contain thousands of these cores for massive parallelism. Special function units, SFUs. SFUs handle complex mathematical operations like sine, cos, and exponential functions, offloading these tasks from CUDA cores. Registers. Extremely fast memory locations within the SM used to store temporary per thread variables crucial for rapid computation. Shared memory, a small, very fast on chip that allows threads within the same block to communicate and share data efficiently, significantly reducing latency. Execution model SIMT. Within an SM, threads are grouped into units called wraps. Typically 32 threads in NVIDIA's GPUs, all threads within a wrap execute the same instruction simultaneously on different data. The model is known as SIMT, single instruction multiple threads, which is highly efficient for high parallel workloads. Now next, GPU memory hierarchy will be explained by my friend Priyanshu.
So, this GPU memory hierarchy, the hierarchy of a GPU hardware starts with the registers, which are the fastest and private to each individual thread. Registers hold local variables that are accessed most frequently during computation. The shared memory, this is the on-chip memory, which is made by a collection of registers shared among threads within the same block, providing very fast, low latency communication and data reuse. L1 cache located inside each shared memory. The L1 cache reduces repeated accesses to slower global memory for frequently used data. L2 cache is shared by all shared memories and serves as an intermediate intermediary between the shared memories and the main global memory VRAM, further reducing the latency. Finally, the global memory, which is the VRAM, the largest but slowest memory component. The VRAM is the primary storage of data, offering hundreds of cycles of latency for access. It is because of these that GPUs are capable of performing trillions of calculations. So the parallel processing, which is the main function of GPU, the workload division is the initial problem, which is systematically broken down into numerous smaller independent tasks. This decomposition is crucial for leveraging the GPU's parallel capabilities. Grouping of threads. Each independent task is then assigned to a thread. These threads are organized into hierarchical groups known as blocks, and blocks are further grouped into grids. Execution in shared memories. Thousands of threads execute simultaneously within the streaming multiprocessors. Within streaming multiprocessors, there are threads executed in WOPs, which are groups of 32 threads, ensuring efficient parallel processing. Synchronization at specific points, threads within a block can synchronize, allowing them to share intermediate results via shared memory. This is critical for tasks that require inter-thread communication. Output collection, once all parallel computations are complete, the individual results from each thread are collected and combined to form the final consolidated output, which is then transferred back to the host, CPU, or display. The result of which we see on our screens whenever we play video games or uh, do any TensorFlow stuff, etc. So the key advantages of this GPU architecture is massive parallelism. The core strength of GPUs lie in their ability to execute thousands of computations concurrently thanks to their numerous cores, which are, for example, in RTX 3080, there are 10,000 something CUDA cores, whereas in our CPUs, there are around max to max 32 cores. So you can see the difference. High throughput GPUs are designed to process a significantly larger volume of data per unit time compared to traditional CPUs, making them ideal for large data sets, which is why they are also used in data science and uh, training large models. Scalability. Performance can be substantially increased by adding more GPUs to a system, allowing for greater computational power as needs grow. Versatility. Beyond graphics, GPUs are highly adaptable for diverse applications including AI, machine learning, scientific simulations, and big data analytics. So, to conclude our presentation, GPU architecture is fundamentally optimized for parallel workloads, excelling in tasks that can be broken down into numerous simultaneous operations. The combination of their thousands of cores, high memory bandwidth, and a sophisticated multi-level caching system makes GPUs exceptionally suited for the demands of modern computation. They are not just for graphics anymore, they are the backbone of rapid innovation in various computational domains. Thank you for listening.